Well, hello everyone. How are you today? We're going to start chapter 10. Guess what? Sequences. To then go into series. Well, I already said in class, but this is a topic that really is important. And why? Because we are going to model, we're going to approximate functions using polynomials. And polynomials are easy for computers to work with. So, let's see. First of all, what's a sequence? A sequence is a bunch of numbers, each of which is called term. And the importance is that we are going to order them. Okay? So it's not just a bunch of numbers, but an ordered bunch of numbers. Okay? So the first one is named A1. Let me put A1. Second one is A2. Third is A3. So unless stated otherwise, our sequences start at 1, okay? If it's specified, a sequence can start at 4, I don't know, 3, 10, 100, whatever. But if it's not specified, starts at 1. And we denote a sequence like this. So A is like the general name of that family. And then a sub-index says if you're talking about the first, second, third, or fourth term of the sequence. If you find this notation, you always assume that n starts at 1 and goes all the way to infinity. N. Okay? A very simple example is, for example, even numbers. 2, 4, 6, 8. So the first one in the list is the 2, that's called A1. The second one in the list is 4, that's called A2. Third one in the list is A3, is 6, called A3, so on and so forth. We can give a sequence by giving what's called the general term. So we all know that all even numbers can be written as 2 times a number, right? Because if it is even, it's divisible by 2. So this would be the general term for all even numbers. You see, when you plug in 1, let's see, if you plug in n equals 1, you get A1, which is 2 times 1, which is 2, first even number. If you plug in n equals to 2, remember n are integers going from 1 to infinity. So these are a bunch of points, no functions, no lines, points. N equals 2 would be A2, and that's 2 times 2, which is 4. And you can see how this determines the sequence called the general term. So sometimes it's easy to find the general term of a sequence, sometimes it's not. Sometimes they give you the list of numbers in the sequence, sometimes they just give you the general term, and then you would be able to give the list. Going from the general term to the list is always easy, just plug in the natural numbers, but going from the list to the general term sometimes can be a little difficult. Okay, so let's see examples of sequences. Let's see. I don't want to use black, let's use purple. So what is this sequence right here? An equals root n. Well, if you want to display that as a sequence of numbers like this, as a list, you would have to plug in first n equals 1. If you plug in n equals 1 here, you get root of 1, which is 1. Then plug in n equals 2, you get root 2. Then root 3. Then root 4, which is 2. Let me write it 2. Then root 5, and so on and so forth. And then you do the dots, and that will give the list of that corresponding sequence. Okay? You can have a sequence like this, where the first digit starts for an n equals to 3. So the first guy in this list is going to be for n equals 3. So plug in the 3 here, and you get 3 minus 1, 2 over 3. 2/3 is the first guy in the list. Next one, of course, go one by one, n equals 4. 4 minus 1, 3 over 4. And then 4 over 5, and then 5 over 6, and so on and so forth. This would be the list corresponding to this general term. So again, you can be given a general term. If they don't specify, you assume n equals 3. If you want to list just the terms 3 and above, you write it like this. Okay? And that concludes the example. It's kind of weird to explain without having questions or anything. Okay. So how do we picture this? Okay, let's do the next one to picture it. Okay. Different types of lists, we're going to analyze how they behave. The idea is, are these numbers, when you go on the list as n approaches infinity, are those numbers approaching a number? Are they growing to infinity? Are they growing to negative infinity? What are they doing? That's a concern. We have sequences like the one, number 4, which is going from negative to positive, negative to positive. You see? Let's display the first terms of this sequence. So for n equals to 1, when you plug in a 1 there, you get negative 1 squared, so it's positive, and then 1 over 1. So the first one is 1. N equals to 2, then it's negative 1 to the third power, so that's negative, and then 1/2. And then positive 1/3, right? For n equals 3. For n equals 4, it's going to be negative 1 over 4, and it continues like that. When you graph a sequence, what you're going to get is points. You're only considering look at a sequence as a function whose domain is just the counting numbers. Okay? So for n equals to 1, you're going to get a dot at 1. That's going to be the first guy in the sequence. Because sometimes graphing sequences is useful to understand what the function is doing. For n equals 2, you would go to negative 1/2. N equals 3 would be 1/3. N equals 4 is negative 1/4. And then positive 1/5. And then negative 1/6. You see that it's going like that, getting closer and closer to 0. Never 0. You see why, right? As n approaches infinity, you are dividing 1 by a huge number. It's never 0, but it's getting close to 0. But it's getting close to 0, changing signs. That's kind of a special behavior of a sequence. These are called alternating sequences because you're alternating from positive, negative, and so on and so forth. Okay? All right. Yeah, I think that's it for this part. Okay, now the question is, as I was saying before, you can go from the list to the general term or from the general term to the list. All these examples here went from the general term and then we listed them. Now we're going to analyze how to go from a list to give a general term. So what we're looking for here is what in the world is AN? How could I specify this list by taking n equals to 1, n equals to 2, n equals to 3. We're given only 4. From there, we have to find a rule for AN. So when you plug in 1, you get 2. When you plug in 2, you get 3 over root 2. When you plug in 3, you get 4 over root 3. Okay? So the tactic here is, well, let's see. We want A1, A2, A3, and A4. So those are the first terms that are given. We start working with that. So the first guy is a 2. The second guy is 3 over root 2. third, 4 over root 3. I don't know if you can see already a pattern here. This is kind of easy to see. So compare to, you're going to compare these numbers that you get here to the n. Because what? You need to write this in terms of n, something depending on n. That's how you want to find the general term, right? For an, this is the formula. So when you plug in the 1 here, or no, the 3 here, you plug in the 3 and you get a3. Okay? So we need to write this in terms of n. So we need to compare whatever number we have here with the 1. And looking in advance, the next numbers. So you see that there's a 2 here that goes with the 2, with n equals to 2. 3 goes with n equals to 3. 3, that should be a 4, I'm sorry. Of course, that's a 4. Which is just 5 over 2. Okay, I'm sorry. That was a mistake there. That's a 4. Alrighty. But you see, it's better to write it like this so we see the pattern. It's root 4. So the n here coincides. How does this compare to the n? So for an n equals to 2, you have a 3. N equals to 3, you have a 4. N equals to 4, you have a 5. So this is adding 1 to the n, right? In this case, the 3. This is adding 1 to the 2. This is adding 1 to the 4. So you can rewrite it, like maybe it's not necessary for you in this example to rewrite it in terms of the 1 and looking at the pattern. So the first one, you can write it as 1 plus 1. This here, I'm going to write is the n over square root of 1. Okay, the second one, we can just do, so the n is 2, and we add 1 to get the 3, right? So we write the n here, 2 plus 1. That makes the 3, and in the denominator, we just have root 2, and that compares exactly as that, as this indices. Then, to get this, you add 1 to 3. So in terms of n, in this case is 3, you write it 3 plus 1 over root 3. And the last one, to get a 5, you have to do 4 plus 1 over root 4. So you see your n here? That's the n. 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 So my general term ends up being n plus 1, so just add 1 to the numerator and take the square root of n in the denominator. And we got the general term. You see, when you display this as a list, that's what you get. N equals 1. You get 2 over root 1, which is 2. When you plug in a 2, you get 3 over root 2, and so on and so forth. Okay. Let's see, how could we write this? What could the general term be? Again, we're looking for general terms here. Okay. So let's display that. I'm going to move this a little bit up so it doesn't interfere with the new example. It's a little cramped here. All right. So let's do A1. A1 is negative 1. Just negative 1. A2 is 2. A3 is negative 6. A4 is 24. A5 is negative 120. So you see, when n is odd, the exponent is negative. So negative 1 to the n will work, because if n is odd, we get negative signs. If n is even, we get positive signs. Unlike this one, which was n plus 1. So the evens got the negative and the odds the positive. Here is backwards. The odds get the negative. So we can write this in terms of 1 as negative 1 to the first power. So I'm taking care of the signs first, okay? Then I'm going to take care of the numbers. The other one would be negative 1, and the n is 2 to the second power. That makes it positive. Negative 1 to the third power, negative 1 to the fourth power, and you see how it works. It's giving me negative, positive, negative, positive, negative, positive all the way, which is what we see here, negative, positive, negative, positive. All right, now let's look at the numbers. How can we write the next number in terms of the previous one? That's the idea. Write it in terms of the previous one, or in terms of the n here. How do you write the new number here in terms of that one? How you write this in terms of that? But you're going to keep the previous one. Let me show you. So how do you write 1 in terms of 1? Well, you keep it. Nothing else to do there. How do you write 2 in terms of 2? Well, I'd say 2 times 1. How do you write 6 in terms of 3? You see, that's 3 times 2 times 1. So you're going to keep the previous one. How do you write 24 in terms of 4? 4 times 3 times 2 times 1. How do you write 120? Okay, if you take 24 and multiply by 5, so if you take the previous one and multiply by n, you're getting the next one all the time. Times 4, times 3, times 2, times 1. Right? So if you see, we're making here something that's called the factorial. I'm going to explain the factorial in detail and show you how to work with the factorial a little later. Okay, so an is going to be negative 1 to what? Is the same n we needed to produce those signs. So this is just n. Negative 1 to the n. And then the number in terms of n is 2 times 1. This is the factorial of 2. This is the factorial of 3. Or let me write it. Let me write the sequence here to have space there. So this is 1 factorial, which is 1. This is 2 factorial. This is 3 factorial. This is 4 factorial. And this is 5 factorial. So we just need to multiply by n factorial here when we get the general term. Notice if you plug in, say, a 3 here, it would be negative, because that would be a 3, negative 3 factorial. And 3 factorial is 6. So you have the third term. And so on. So a little later, I'm going to go exactly into the factorial when we get to really use it more. So just remember that the factorial of n is when you multiply n times the previous number times the previous number until you reach 1. Okay? Then we'll see how we work those. Okay, so we talked about a sequence given by a series of numbers. It's, well, not a series, a bunch of numbers. But the important thing here is that they are labeled by the counting numbers. They are by the natural numbers. They're labeled by 1, 2, 3 in that order. And then we can talk about its behavior, like this one. You see, it is approaching 0. It's jumping, but approaching 0. The other way you can give sequences is by recursion. A recursive sequence tells you the next one given the previous ones. So they give you the first 2 numbers, and then the next number in the sequence has to do with the previous 2 numbers. You see? the term an plus 1 is given in terms of an and an minus 1. So if we want to display a list here of numbers, okay, what is an? Like a list. Well, a1 is 2, that's given. And a2 is 4, that's given. a1 and a2. How do you find a3? I guess you already know, right? So to find a3, you're here. a3 is a2 plus 1, right? That's the n plus 1. So n is, the n you're going to use here is 2. So that's going to be 2a2 minus a1. And because those are given, it's 2 times 4 minus a1 is 2, right? Just replace a1 here, a2 here. And that is what? 8 minus 2, which is 6. So that's the next number here. That's a3. How do you get a4? Oh, you have to write it as n plus 1 because that's the formula you have. 4 is 3 plus 1. So n is 3. So 2a3 minus a2, the two previous elements of the sequence. So that's 2 times a3 was 6 minus a2 was 4. So that's 12 minus 4 is 8. Oh, what are we getting here? Let's see a5 to see what we're getting here. 4 plus 1, that's 2. A4 minus a3. 2, a4 is 8 minus a3 is 6. And that's what? 10. Oh, we found another way to list the even numbers. But this is given in a recursive way, whereas this is given with one general term. Capisci? And then the most famous ever, the Fibonacci sequence. I love it. There's so many things. I would like for you to Google Fibonacci sequence, because there are so many things in nature that follow the Fibonacci sequence, like the way rabbits are born. They start one and then they grow in this pattern, like the Fibonacci sequence. So let's look at the first few terms of the Fibonacci sequence. If we want to list the terms here, you realize that it's very easy, because what is it saying? It's saying, take the first term to be 1, the second to be 1. But then the next one, the n plus 1, is take the two previous one. So previous to n plus 1 is n, and previous to that is n minus 1. So take the two previous one and add them. Here you don't have to write formulas. I mean, it's completely obvious. The next one here is the addition of the previous two. So it's 1 plus 1. That's a 2. The next one here is the addition of 2 and 1. So that one is 3. And then 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13. 13 plus 8, 21. 21 plus 13, 34. And so on and so forth. That would be the list of the Fibonacci sequence. And this is the Fibonacci spiral, which is amazing how it's done, right? You start with 2 squares. You see the Fibonacci sequence? No, let me use the highlighter. Fibonacci sequence starts with 1 and 1, right? There, a square for 1 and a square for 1. Then you're going to graph this square, whose side is the addition of the previous 2. And you make a square. So now take that length and make a square. Now you're going to make a square here where you add the side of the 2 previous ones, which are 2 and 1. And you make that, and then take the length and make a square. Then you're going to make a square here, which is the previous one, the previous 2 elements. You get a side of 5 and make this rectangle. And so on and so forth, you see? The previous ones, 5 and 3, take that length and make a rectangle here. The previous 8 and 5, make that rectangle. Previous 8 and 13, make this rectangle, and so on. And then you join the corners. So it is missing here, but you start with this corner. Okay, let me put it smaller and maybe black. You go from this corner to this corner to this corner. It's really like that. I don't know, that little piece is missing. So you see, this is the Fibonacci spiral. And there are many things. So I don't know how many things have that shape in nature. Of course, a snail. That's the first one that comes to mind. But the way the petal of roses are distributed, they follow that. Pine cones follow the Fibonacci spiral. So this Fibonacci spiral is so much in nature. There are plants that look exactly with this shape, like that. And not only that, but if you see like a cello, a violin, and you see the head, the shape is like that. Because in architecture and in crafting, this is the most aesthetic spiral. Compare that to a normal spiral like that. This is not aesthetic at all. It's just like concentric. That's a normal spiral. Look at this one. This is all elegant and it opens like very elegant. And that is what instruments like cellos, violins, basses have heads like that. And that's the Fibonacci sequence. I really would like for you to Google that. And you'll see so many things coming up with the Fibonacci sequence. So as I said, we're interested in the behavior of these sequences. In this example, this sequence approaches 0. So you can imagine that you can have different types of sequences. You can have a sequence like this. Sorry, because now it's not like this, where the numbers are approaching 0 from above, or 1 where they're approaching 0 from below. Or you can have sequences that are constant, like, I don't know, like that, okay? Or sequences that, I don't know, go like a line, or like e to the x, well, faster, but something like that, okay? And we want to analyze that behavior. Special interest is if they converge to a number. That one over there would not converge to anything. That's going to infinity. We can have one going down also. This one is converging to that number, right? One that goes like this would be converging to 0. Maybe one that looks like this is converging to 1 right here, okay? And that's what we're going to be analyzing now. That's what we're interested in. Convergence and divergence of sequences. So this is just asking, what is the sequence doing when you let n grow big? So in other words, it's the limit as n approaches infinity of all those numbers. Okay? We're going to use our knowledge of functions later on to be able to find these limits. But in essence, you do find the limit with the same properties that we had for limits of functions. Okay? First thing is that when we take this limit, if the limit exists, then the sequence is convergent. Remember, a limit exists if it is a number. So if it's infinity, the limit does not exist, okay? Because infinity is not a number. So it exists only if it's a number, okay? So two possibilities. It does not exist because it's jumping and not approaching anything, or because it goes to either positive or negative infinity, okay? If not, if it doesn't approach a number, we say that the sequence is divergent, okay? Just like we did with improper integrals. Same concept, different guys. but related, guys. Different but related. And you'll see later how they relate. Okay. Properties. These properties, come on. You already seen these properties all over the place. The constants, when you take the limit of a sequence, so that is what is the sequence approaching as you go to infinity, the constants come out. Property 1. The limit splits over addition. Property 2. The limit of the multiplication is the multiplication of the limits. Property 3. Property 4. The limit of the quotient is the quotient of the limits, provided that this is non-zero. Of course, if the denominator approaches 0, then that will not exist. And then the limit enters the powers. Okay? The limit of a power is the power of the limit. Okay? So let's see a couple of examples of sequences to see if they converge or diverge. As you can see, the sequence of natural numbers itself, so this general term would be an equals to n. 1, 2, 3, 4, that goes to infinity, come on. That absolutely, no doubt, diverges, going to infinity. The negative numbers, that's going to negative infinity, that diverges. Okay? No, but what happened with the property? And what's happening here? What happens? Because if we add the two sequences, and the addition of sequences is defined to add term by term, okay, but if you add them term by term, and you have this property that it splits over addition, but if you add this to this one, you get 0 everywhere, which of course approaches 0 because always 0. What happened? What happens is that you can have two divergent sequences, and even though both are divergent, the addition of the two sequences might be convergent. So this is an example that tells you that. Okay? You can conclude that if these two are convergent, then this is convergent. You can conclude that if one is divergent and one is convergent, this is divergent. But you cannot conclude if this is divergent and this is divergent, that this one diverges. You can't say that, and here's an example. So addition of convergence is convergent, but addition of divergence is not necessarily divergent, as you can see in the example. Let's analyze more convergency and divergency, and this is just going back to limits. But now you use the same ideas you did for limits of a function with an x, but now substitute the x by an n. Now n is a natural number, going to infinity always. So this is more of a limit refresher than anything else, because if you have the general term, you can take the limit, right? Because the general term, it's how you describe each of the elements of the sequence, okay? So in this case, you see the sequence here is jumping, but it's jumping from, unlike the other one, it's jumping from -1 to 1 to -1 to 1, and like in that fashion forever. Oops. Forever, right? That thing is jumping. It will never converge to anything. So this is divergent. You see the limit as n approaches infinity of -1 to the n does not exist. So the corresponding sequence is divergent. Okay? To analyze the rest, you do the same. You take the limit as n approaches infinity of the general term, in this case 2n over n plus 1. Go back to your basic knowledge of limits. Remember the limit as x approaches infinity of 2x over x plus 1. This is a rational function, and this is a horizontal asymptote. The degrees are the same, 1 and 1. So you have a horizontal asymptote at the limit. Remember, if you have the same degree here, the limit is the quotient of the coefficients. So the limit here is 2 over 1, which is 2. So you're going to do the same here. You see, same degree, the limit is going to be 2. That's one way of doing it. Say you don't remember that, well, then apply what we did in Calc 1, which is, let me bring this a little bit, okay, which is divide top and bottom by n, everywhere by n. This would be the proof, right? So when you divide everywhere by n, which is a legal step to do, and this is infinity, not 0, then you get a 2 on the top, a 1 here, plus 1 over n. And when n approaches infinity, this approaches 0, and your limit is 2. So the sequence is convergent. All right. Let's look at the next limit. So to determine if these sequences are divergent or convergent, you have to take the limit. Okay, that's n. So let's split it into, or not, let's just do the same technique. Divide everywhere by n. So you would have 2 over n plus -1 to the n over n over n. Why I do that? Because it's a technique that you can apply anytime you wish. Why I did it? Well, because I know that if I divide this by n, I get a 1 down here, I get a 0 here, and I will just be left with this guy here to analyze. That's why I did it. Let me erase this. Put it here, convergent. Okay. So when you take the limit, this guy here would be 0. This here is 1. Okay. And then this limit is 0. This is the same example we wrote up here, right? -1 to the n or -1 to the n plus 1. It just switches which is up and which is down, but the behavior is the same. It's like that. Approaching 0. Okay. Later we're going to prove it. But that is obviously approaches 0. So this guy approaches 0 over 1, which is 0. Thus, that sequence is convergent. Okay. So again, this is like a practice of limits. Go back and review your limits if you're lost at this time. So how do you find the limit as n approaches infinity of root n plus 1 minus root n? So if you remember calculus 1, this is an indetermination of the form infinity minus infinity. That indetermination, you have to think what to do. And what you have to do here is multiply and divide by the conjugate, remember? Every time you have root something plus something, or 2 roots adding, 2 roots subtracting, you multiply by the conjugate to get rid of that indetermination. So you take the conjugate, which is just changing the sign, and multiply and divide by that. Then on the top, you use the difference of squares formula, which is the square of the first one minus the square of the second one. And the bottom just stays like that, but notice that this is infinity, that in the bottom we just have infinity. Okay, not undetermined. The bottom is just infinity. Now let's look at the top. Cancel those things. Right, this cancel out. N plus 1 minus n over, same thing, root n plus 1 plus root n. when these cancel out, you get this limit, which we can take now. 1 over root n plus 1 plus root n. Because the bottom approaches infinity and 1 over infinity is 0. So we proved that the limit is 0, so that sequence converges. Is convergent or converges. So if the limit of the sequence is a number, it converges, otherwise it diverges. So you can see that here we have to go back to limits, just refresh them, because you're doing the same thing of limits we did for the variable x, but now the variable is always an integer going to infinity. Okay. I don't know if you remember the sandwich theorem from Calc 1. It said, well, if you have a function here and a function here, this is always on the top, this is always on the bottom, and you have a function in the middle one gets squeezed by the top and the bottom. If the limit of the top and the bottom at certain point is the same, then the middle one gets squeezed in between, and we'll have to have the same limit at that point. Okay? So this is what's happening. Here's kind of a picture for sequences of the same situation. So you need 3 sequences, okay, of real numbers. 1 sequence in between the other 2 for all n's. Before was for all x's, here is for all n's, okay? And if that happens, if you have 3 sequences like that, with this inequality for all n's, then if the limits of these 2 are the same, the middle one gets squeezed or sandwiched between the other 2 and would also have to have the same limit. So if this limit is L and this limit is L, the middle one must be L. Okay? So if the absolute value of a function is less than or equal to a sequence, if you have something like this happening and that sequence approaches 0, then what happens? An gets squeezed in between, because what does it mean for an absolute value? For absolute value of x to be less than 3. That means that x is between -3 and 3, right? So this means, this right here means that an is between -cn and +cn. But if cn approaches 0, that means that an gets squeezed between -cn, that is approaching 0, because if cn approaches 0, -cn approaches -0, which is 0, right? So this approaches 0, this approaches 0, then the middle one has to approach 0. So if the absolute value of the sequence is less than cn and cn approaches 0, then an approaches 0. We're going to use that later on. But it's kind of a very neat result that we get straight from the sandwich theorem for sequences. Okay. Another way to write limits is like this. This would be missing. You would have to write n approaches infinity, okay? So you don't have to always, when you're dealing with sequences, write the word limit as n approaches infinity, but you can just write this, whatever is appropriate. In this case, whatever the arrow is. Okay? So let's prove this using the sandwich theorem. But come on, this is easy, because you know that cosine n, no matter what n is, it's always between -1 and 1. Now the n's we're dealing with are positive numbers, so it is okay to divide everything by n, right? It will not change the inequality because n is positive. Maybe I can write it here. Okay. N is positive, okay? Because n is positive, you can divide by n everywhere. Now you see that this approaches 0. As n approaches infinity, -1 over n definitely approaches 0. And here, 1 over n approaches 0 as n approaches infinity, right? So the middle one must approach 0 by the theorem. And we have proven that this approaches 0. So if we can squeeze our sequence between two sequences that approach the same number, then the middle one has to approach the same number. So here's just the ability to be able to bound whatever you have here by two sequences on the two sides that have the same limit. How could we operate with 1 over 2 to the n? Like the comparison test. You need to bound it, and you need to start from something that's true. And it is true that 2 to the n is always bigger than n. That is for sure. Right? Okay. Now, if you take the reciprocal, because that's what you need, the reciprocal of 2 to the n. So you bound by something smaller. If you take the reciprocal, 1 over 2 to the n, the inequality is going to flip. 1 over 2 to the n is going to be smaller than 1 over n. Okay? Okay? But we also know that 1 over 2n, this is an exponential function. 2 to the n is always positive. 1 over 2 to the n is always positive. So this is always bigger than 0. Okay, 0 approaches 0 as n approaches infinity. Let me write that better. I can hardly understand. As n approaches 0, 0. And as n approaches infinity, 0 approaches 0. And as n approaches infinity here, 1 over n approaches 0. So 1 over 2 to the n, so by the squeeze theorem, the middle one gets squeezed and should approach the same limit that the ones on the ends. Okay, like that. So we showed that 1 over 2n approaches 0. Okay. This is a direct consequence of this. So if the absolute value, but it says a lot, okay? If the absolute value of a sequence approaches 0, then the sequence itself approaches 0. That's a lot to say. Okay, it comes from here. Other way of writing it. So that allows for us to remember I told you we were going to show that this limit is 0. Okay, now we have a tool to prove that, because if the absolute value approaches 0, then the sequence approaches 0. Okay, let's take the absolute value. Not equal, I'm sorry. Take the limit of the absolute value. If we take the absolute value, what's the absolute value of that? Well, always the positive 1, right? So that's 1 over n. And we are sure that this is 0. By this result, negative 1 to the n over n approaches 0 as n approaches infinity. Alrighty. So we proved that limit. This is long. It's taking me some time. I don't know how long is this video so far. Okay. The continuous function theorem, very important. This is when remember when I told you that sequences are related somehow to functions? And because a sequence is a function, only that the domain is not all real numbers, it's just the natural numbers. Okay, if you see it like that, they are functions. So suppose you have a sequence of real numbers, okay? So these are a bunch of real numbers. And the sequence approaches L. If f is a function that is continuous at L, and it is defined for all ANs, so your function is defined for all ANs, and AN approach L, then the function approaches L. It's like you can take f here and here, all right? So if AN approach L, f of ANs approach f of L. And that's very important. It will allow for us to find if sequences are convergent or divergent by using our knowledge of functions, okay? So how do we do that? Let's show that this approaches 1. So we have to take a limit there. So what we know, because we did it divided by, we can do it by dividing n, is that the limit, or let me write it like that, that n plus 1 without the square root approaches 1, right? If you want to have a proof, you just divide everywhere by n, divide everything by n. That would be the technique to apply here for a proof, right? That's the limit as n approaches infinity of 1 plus 1 over n over 1. And this approaches 0, so this limit is 1. Okay, that would prove this limit. So what the theorem says is that if the function f is defined for all these numbers, taking f of this would approach f of that. So in order for us to go from this that we know to this that we don't know, you need to take the square root there. So consider f to be root x, that function. So you're going to be evaluating f at the integers, right? So f of n plus 1 over n by the theorem approaches f of 1. This is by the continuous function theorem. And by the way, this is continuous on its domain. We don't care about the domain because what we are going to input here are positive numbers. Look, they are positive numbers. So we're fine. By the theorem, we get that. Well, what's f of 1? F of 1 is root 1, which is 1. And what's f of this? Square root of that. And we have proven using the theorem that as n approaches infinity, root n plus 1 over n approaches 1. Make sense? No, you cannot answer me here. But well, I hope it makes sense. Let me reduce the size here because it's kind of big. Okay, let's do example 2. Example 2. The limit as n approaches infinity of sine of 1 over n. So do you see that this theorem is the one that's going to allow for us to say, well, 1 over n as n approaches infinity approaches 0, then sine of 0 is 0 and e to the 0 is 1. So this limit must be 1, okay? For that, you use that e to the x and, e to the x and sine of x are continuous, both. Because this is continuous function theorem. To apply this theorem, we need continuity at the point. Sine is continuous at 0. E to the x is continuous at 0. Okay? At that limit. at that limit here, which is 0. Okay? But we know that 1 over n approaches 0 as n approaches infinity. Then, by the theorem, if you take e to the sine, let's take f of x, e to the sine of x, that is continuous because it's a composition of continuous function. So if you take this on both sides, you get the limit, right? So if 1 over n approaches 0, e to the sine of 1 over x, so let me write this, you might get confused. So f of 1 over n approaches f of 0, right? It's like taking, if this approaches L, f of this approaches f of this. So this is approaching 0, and f of this approaches f of 0. You get it? What is f of 1 over n? Well, plug in 1 over n here. That's what we had. That's what we want to find. So that is e to the sine of 1 over n. That approaches f of 0. So that approaches e to the sine of 0. Sine of 0 is 0, and e to the 0 is 1. So it approaches 1. We found that the limit as n approaches infinity of e to the sine of 1 over n is 1. So in other words, this theorem is allowing for us to take the limit from the inside out, as we do with functions, take the limit of the sequence, and then take the function evaluated at the limit, and then the other function evaluated at that limit. Okay? This is what this is allowing for us to do. Okay, now the other example is tan inverse. I recall here, how does the graph of tan inverse looks like? I don't know if you remember. When you invert the tangent, you restrict the domain from negative pi over 2 to pi over 2. That's going to be your range. And then the function is doing that. So tan inverse approaches pi over 2 as x approaches infinity, and as x approaches negative infinity, tan inverse approaches negative pi over 2. Okay? So when you try to take this limit, you can take whatever this is approaching and then take tan inverse of that. That's what the theorem says, that we can do that. Okay? So we know that tan inverse of x is continuous. Continuous everywhere. Continuous. That, well, let's put continuous. Okay. That is continuous. And we know that the limit as n approaches infinity of n squared is infinity. And then the theorem is going to allow for us, even if it's infinity, to take tan inverse of that. Tan inverse, tan inverse. Okay, so limit as n approaches infinity of tan inverse of n squared as n approaches infinity is going to be like plugging in infinity here, and tan inverse approaches pi over 2 as you approach infinity, so this limit becomes pi over 2. That's what this theorem allows for us to do. Take the limits from the inside out, from the sequence to the functions. Okay? That's the continuous function theorem for sequences. And now this other theorem, what does this theorem say? Suppose that f of x is a function defined for some x. It doesn't have to be defined for n specifically starting at 1, but starting at some integer n called n0 here, okay? And suppose that this sequence is a sequence of real numbers that comes from a function. So let's see a little bit how that looks like. Suppose you have the function f of x equals 1 over x, the reciprocal function. Then you can always evaluate your function at n, at an integer. So at 1, the reciprocal function is 1. At 2, the reciprocal function is 1/2. At 3 is 1/3. 4, 1/4, and so on. You see, if we evaluate one function only at integers, we get a sequence, okay? And that's what it says here. Suppose that the sequence is coming from a function that has been evaluated at integers, okay? If that is so, if you can write the general term as a function evaluated at n, then if the limit of the sequence is L, the limit, then the limit of the sequence is L whenever this is L. So if the limit of the function was L, like here it was 0, if the limit of the function is 0, then the limit of the sequence is 0. In other words, the limit of a sequence coming from a function is the same as the limit of the function. So if the limit of the function is 0, the corresponding sequence is going to have a limit 0. If the limit of the function is infinity, the limit of the sequence is going to be infinity. Okay? That's what it says. So knowing that, we can find a lot more sequences. We can find if many more sequences converge or diverge. Okay? Let's look, for example, ln n over n. This is what allows for us to do L'Hopital for sequences. This theorem is allowing us, it enables L'Hopital's rule. Why? Because it doesn't matter how you take this limit, if you had to derive or anything, but then the limit of the sequence formed in that way will converge to the same L. Okay? Because here you can derive, but here you can't. Because remember, the derivative, it's an approximation. The derivative is done over all real numbers. Okay? But this is not. But this theorem tells us that we can derive just the same way we did it for x. This is telling me, okay, go ahead and derive this. Okay? In the same way, like if the n was an x. That's all that's saying. So if you analyze this limit, this is approaching negative infinity. Sorry. No, that's at 0, honey. ln is approaching infinity as n approaches infinity, and n is also approaching infinity. So we have an indetermination of the form infinity over infinity. Okay? And we then apply L'Hopital, because that is a L'Hopital indetermination. Okay? Derive the top, the derivative of ln n is 1 over n. Derive the bottom, which is just 1. The derivative of n with respect to n is 1. And then let n approach infinity. So 1 over n approaches 0. Then this would approach 0 over 1, which is 0. And we found that the sequence is convergent. It approaches 0. It's approaching a number. And here, these problems, so once you know the theorem, you know you can apply L'Hopital. This is just refreshers of how do you find limits, okay? Refresher of L'Hopital's rule. So the inside of this, as you approach infinity, is 1, right? You see same degree, 1 and 1. So you treat this like you do with an x, okay? With real numbers. So that's a 1 and this is a 1. Okay? So this limit on the inside is 1. And this would be infinity. 1 to infinity is an indetermination. I hope you know how to get rid of that indetermination. If not, you have to go back and review. So we rewrite using ln. Remember, when things are in the power, we need to bring them to the front using ln to be able to work them out. So we take ln on both sides. Ln of an equals ln of n plus 1 over n minus 1 to the n. Then we apply here the property of ln, that the powers multiply to the front. So that's n ln of n plus 1 over n minus 1. Okay. And now this indetermination that was 1 to infinity turned to the indetermination infinity times 0. And that's always the case when you do this procedure, because if this is infinity and this is 1, L of 1 is 0, and that goes to that place, that's going to always be infinity times 0, which is again an indetermination. But we know how to get rid of that indetermination, right? Infinity times 0. We've done it in class. So you flip one of them. Of course, you don't want to flip a ln, you want to flip this one. And then the limit as n approaches infinity of ln of an is what? We're taking now this limit, okay? Is what? Is the limit as n approaches infinity of n ln of n plus 1 over n minus 1, which is an indetermination of the form infinity times 0. And we can use L'Hopital, but we have to rewrite it to use L'Hopital as ln of n plus 1 over n minus 1 and flip the bottom one. So now this approaches 1 and n of 1 is 0, so it's 0 over n approaches infinity, so 1 over n approaches 0. So now we have an indetermination of this form 0, so over 0, and we can apply L'Hopital because it is a L'Hopital indetermination. So derive the top and derive the bottom. The bottom is negative 1 over n squared, if you remember. On the top, you have to use the quotient rule. So low d high minus high d low, square the denominator, and away we go. Remember? Okay. So just derive here. The derivative of n plus 1 is 1. So we have n minus 1 here, minus, and then the derivative of n minus 1 is 1. With this negative sign, we get negative n minus 1. So the n's also over n minus 1 squared. So the n's cancel out, and this would be the limit as n approaches infinity of negative 2 over n minus 1 squared. This is just algebra, as you can see. For n squared, reciprocate and multiply. The two negative signs, it's going to make it positive, so I'm not going to write that. Keep the top, reciprocate and multiply the bottom, right? I'm just checking that everything is fine. Wait, what happened here? Let me check. Blah, 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 and -1. Oh, they did it differently. They did it differently, but I think we get the same answer anyway. And that is 2n squared over n squared plus 2n plus 1. Then you have a rational function with the same degree. The limit is the limit of the coefficients, so the limit is 2. I don't know what they did there. Give me a second, let me check this. I think there's a mistake in the handout. Okay, so the limit is 2. Now, e to the x is continuous, right? And let's recapitulate. We're trying to find this limit, right? We needed to bring this down. So for that, we applied ln on both sides. And we found this limit, okay? So what we really do is to take the limit as n approaches infinity of simple an. What we're going to do is rewrite it as limit as n approaches infinity of e to the ln of an. Because remember, these are inverse functions, so this is exactly that, right? And this limit we already know by the previous theorem. Because e to the x is continuous, we can take e to the limit as n approaches infinity of ln of an. And we found that this is 2. So that's e to the second power. And we found the limit of this thing is e to the second power. So it is convergent. A little long, but doable. I think it's nice. Just have to recall that. Then you have to recall all the limits. No, you have some here that you're going to use. And I'm going to teach you now how to use them to go quicker on finding these limits, okay? Some of them we did here, like this we did. This we know. This is, I don't know if you remember that one, but this is the definition of E. It's also used a lot in business now, in finances. So we have all these limits. What we're going to do is use these limits for particular x's, okay, to find the limits of the examples we might want to find, okay? So these are examples of these limits. You see, the limits here are given in general. So you can use this theorem to just say that the limit of the square root, the nth root of n is 1. But you can also say it as long as the absolute value of x is less than 1. If you have 1/2, 1/3 there, you would just say, okay, that limit is 0. X to the n over n factorial, for example, if x equals to 2, you can say that limit is 0 because this is for any x. Again, here, if you put a number there, like 10, whatever, and here, then you can say that this is e to the 10th power because this is for any x. And that's how these limits are taken, okay? So, like, you have to figure out your way to go from some limits, whichever you get, to one of these and use them. Like this one here, ln of n squared. It looks a lot like that, but it is not because the n is not squared. But we know a property of ln that brings the 2 out. So if the 2 is outside, now you can use it, right? This is exactly that. And that's 0 times 2, which is 0. You see, it's not a rocket science. It's just figuring out how we find this limit from the ones that are given here in general. Going from the general to the examples. Okay. They call it Formula 1, Formula 2 to give it a name and then be referred to that, but those are not things you have to remember. You remember these things, some of those. Some of those are kind of things we know, right? Like if this is a fixed number, the factorial grows much faster than x to the n, so that approaches 0. If x is between 0 and 1, and you raise it to the nth power, a number between 0 and 1, like that, to the n, it's going to approach 0, of course. All right. Now, example B. What looks like example B? Maybe this one here. It's almost that, but it has a 2. Oh, but we know how to rewrite this as a rational exponent, and then the power of a power. And there is our limit. This limit inside is 1, right? So we know that this is 1, and then you square them using the theorem, and you get 1. You see how you apply them? This one right here. Oh, n and n and 3. Okay, let's see, where is that? Well, you have a number here, so when you see an x here, you relate that to a number. So that's a number to the 1 over n, and this is n to the 1 over n, and here I have n to the 1 over n. N to the 1 over n, or the nth root of n, is the limit is 1. And 3 to 1 over n is also 1. So we split it, and we write it like this. From here, that's 1, and from here, that's 1. So the limit is 1. You see how you use them? Not difficult. Example D looks like this one here. This is a number whose absolute value is between -1 and 1. So the absolute value is smaller than 1, because the absolute value is just 1/2. That's smaller than 1 and bigger than 0. So you just plug in 1/2 here, and you get that the limit is 0. Okay. And this looks more like this one. Split it like this, so it looks more alike. And then when you split it, n over n is 1, and then you get -2 over n right here. -2 over n. Oh, I didn't want to go so far. So you see, this thing is exactly this thing, but the x, oh, I'm sorry. Before I said a 10 here, no. If you have a 10 here, you would have a 10 here. I was sloppy, I'm sorry. Yeah, the 10, the number, you think the number is the variable, because the limit is going from n. So this is fixed, but it's working for any x, okay? So it's x the one you think as a number, and the x is here. So this limit is this limit for x equals -2, you see? So what you get as a limit is e to the x you inputted there. So e to the -2. Okay? And then you can see that this looks exactly like that one over there for x equals 100. So think of the x in this list as a number. And then you can find all these limits, because that is what we're going to be dealing with. Okay? I don't know how long is this video, but well, at least we get rid of the first section, which I think is one of the largest. The first is the largest one of all. Many new things coming on here. Let me see. Okay. Well, just one page, maybe 20 more minutes. This is gonna be a long one, come on. Okay, I'm already tired. So suppose AN is a sequence, and what is a bounded sequence? What is a bound? A bound is like a point, a number that you are not going to surpass. This is an upper bound. So all the points on your sequence, if they are bounded by this number here, is because none of those numbers in the sequence are larger. They do not surpass that bound. And the lower bound is a number below, where all the elements of your sequence lie above. So if your sequence is all below a line like this, a number like this, we say that it is bounded from above. And if all the points in your sequence are above one number, then we say it is bounded from below. Okay? And if all the numbers of your sequence are both below one number and above another number, then we say it's bounded. So for a sequence to be bounded, it has to be bounded from below and also bounded from above. Okay? So that's what it says there. So a sequence is bounded if it has both bounds. Let's look at examples. AN equals N. What would you say? Is it bounded from above? Is it bounded from below? Does it have a least lower bound? One that is the largest lower bound possible? What happens with that sequence? Remember, that sequence is 1, 2, 3, 4. It goes to infinity. So definitely it's not bounded from above, because this sequence looks like this, right? It is not bounded from above. But it is bounded from below by 0 or 1, right? What is the largest bound? 1, because that is an element there. And then the rest are all bigger than 1, okay? So it is bounded from below by 1, right? This 1 here is bounding it. This is the lowest term of the sequence. It happens to be on the sequence. Okay, what else can we say here? Is it bounded? No, because you see, for a sequence to be bounded, it has to be bounded from above and from below at the same time. It is bounded from below, but not from above. So it is not bounded. Okay. What are the terms of this sequence? Next example. That's for n equals 1 is 1 over 2, then 2 over 3, 3 over 4. You see how they're going? 4 over 5, and so on and so forth. So if we picture them, let me get another color. If we picture them, we have 1/2 to start with. For n equals 1 is 1/2. For n equals 2 is 2/3. So that's a little more than a half, right? Just a little. And then 3/4, a little more. And a little more. But the numerator is always, it's always smaller than the denominator, so it will never be 1. But it's getting really close to 1. You see? It is really getting close to 1 right there. So 1 bounds this from above. By 1. It is bounded from below by 1/2 would be the highest. It is bounded by 0, by -1, but any number, but the highest one is going to be 1/2. Okay, that is called the maybe largest lower bound. One-half. Okay. So because it's bounded from above and it's bounded from below, this sequence is indeed bounded. Okay. So you can take a rest at any time and then come back because this is getting long. So every convergent sequence is bounded. This is true. Imagine if it's converging, it's because as you go to infinity, it is approaching a number. Okay? So remember, we're starting from 1, then 2, then 3. If it's bounded from above, and that is really far here or here, it doesn't matter. What matters is what happens from one point on. Okay? So if it's bounded from above and from below, all the points, if it's convergent, right, to a number, all the points are approaching a number. That means that's going to be the upper bound, okay? And then the lowest is going to be just a precise number down there. But every convergent sequence is bounded. Not every bounded sequence is convergent. For example, the one we had before, -1/n. Not every, I'm a little tired. So not every bounded sequence is convergent, like -1/n, exactly. So that's 1 and -1/n, that's -1/2. You see? It is convergent to 0, but it is bounded. Oh no, not this one, sorry. Yes, I'm definitely tired. Okay, not that one. The one that's 1, -1, 1, -1, 1, -1. Okay, that's -1 to the end. That is not convergent. It is, jumping like that. It doesn't converge to any number, but it has an upper bound. It never goes up 1. And never gets below -1. It's bounded by -1 and 1 all the way, but is not convergent. So a convergent sequence is bounded, but not every bounded sequence is convergent. Okay. So what is a monotonic sequence? A monotonic sequence is a sequence that's always non-increasing or non-decreasing. So for us to allow the equal sign, we don't talk about increasing or decreasing. We talk, instead of saying increasing, we say that it is not decreasing to allow the equal sign there. Okay. So a sequence is non-decreasing. Is what happens. If it's not decreasing, it's because it's increasing or equal. Okay. And that means that the next term is larger than the previous, so it's going up. In that fashion, in this fashion, I don't know, but it's going up. Because the next term, the n+1 term, is bigger than the previous one for every n. So if you start here, the next one has to be higher, and the next bigger, and the next bigger, and so on. That means non-decreasing. And non-increasing, of course, the opposite. the next one in the list is smaller than the previous one. So you start here, the next one goes down, the next one goes down, the next one goes down, 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 down. The sequence is called monotonic if it's either non-increasing or non-decreasing. And that means for all n, this is happening. It's either non-increasing, non-decreasing, or non-increasing. We call it monotonic because it is like monotonous. It's always going down or always going up. That's a monotonic sequence, always going up or always going down. So let's look at some examples of monotonicity. This is called monotonicity of the sequence. Okay. This is certainly monotonic. You see, this term is bigger than that. This is bigger than that. So the next term is always bigger than the previous one. So this is non-decreasing. Okay. This one is constant. So it's both, because we are allowing the equal sign on both. So it's both. It's non-increasing and non-increasing and non-decreasing, both, because of the equal sign in the definition. Okay. Now let's look at the other example. This one right here. This is the like this one, right? It is approaching 1 because the numerator is always smaller than the denominator. But as you move 1 more in the top and in the bottom, you get a slightly larger and larger number. Okay. So this thing is non-decreasing because the next one is larger than this is larger than that, and so on and so forth. And this thing here goes like this is this example. It goes 1, -1, 1, -1. It's going, so this is larger than that, and then this is smaller than that, and you know, it's jumping up and down. So that is just not monotonic. Okay, it's neither increasing nor decreasing. It's going up and down. Okay. So here's where we want it to go, to the monotonic sequence theorem, which says if a sequence is both bounded and monotonic, then the sequence is convergent. Why we need to do all of this? Because we are finding a criteria to find convergency. Even if we don't know how to find the limit, if we can bound them from above and from below and show that they are monotonic, then we would know that they're convergent. Okay? So that's the idea. A monotonic sequence that is bounded, it's going to be convergent because there's no other way. If it's bounded from above and from below, if it's non-decreasing, it has to stop before the bound, so it's going to approach that, right? And if it's non-increasing like this, then it would have to approach that because that's a bound. It doesn't go below m, it doesn't go above lowercase m, and it doesn't go above uppercase m. So it must converge. That's the theorem. How do you use the theorem? Well, you have to show what it says, that you have a sequence that is both bounded and monotonic. Then you can conclude it's convergent. You don't know where is it going to converge, okay? So how do you show that this is convergent? Well, guys, I guess I'm going to leave it here. You get the idea of what this is. I'm tired, so I'm going to leave the video here, and I think it's enough for you too. And we're finishing class. Okay? All right. See you later. All right. Bye-bye.